Okay, so we can thank the speakers again, please. So next up, we have a talk on deploying MVAPICH with Spack, new features and future plans. Dr. Nathan Hanford, who's a computer scientist in the computing division at Lawrence Livermore National Lab. His research is currently focused on application development, environment portability for parallel software applications. This is at the application binary interface level. His operational work is focused on the development, environment design and verification, MPS support and development, system-wide accelerator-aware interconnect benchmarking for core design, acceptance, and strategic decision-making. So over to Dr. Hanford.
Okay, hello everyone. Yeah, I'm Nathan Hanford. I also wanted to make sure I put as co-authors Greg Becker from the Spack team, and then Nick Sly, who's also in the development and environment group at Livermore, have been major contributors to this work. And so there's as much a part of this as I am, along with a lot of other people on the Spack team. So let's just jump right in. I don't know if any of us really build MPIs correctly, right, for production, right? I think a lot of us get RPMs. We do some testing, run a few smoke tests. We hope we have ABI compatibility. We hope the builds are correct, and then we ship it. And so we really wanted to get away from that in the future, and so we have this sort of workflow goal for us that we'd like to be able to do. So first, let's say a new MVAPICH release is made available. Source code or possibly binaries, if it's MVAPICH Plus or GDR, are made available. The MVAPICH team updates their Spack package, so they have the correct variants if needed, and they also show the correct versions. The trusted source is validated somehow, so we know that this isn't malicious code is in there, and so we know everything's good to go. Once that package is merged by the Spack maintainers, ideally that would kick off continuous integration testing right away, so we could get ahead of any issues that may come up with our cluster compatibility issues. So, and that this would happen on several clusters, because at Livermore we have a lot of different interconnects and a lot of different setups. We have a combinatorial build with different compilers, different accelerators, fabrics, architectures. We're doing two different schedulers now. We have Slurm and Flux. So we need to do integration tests with those, make sure we can launch, make sure we're not getting everything on CPU 0. We have our own smoke tests called Goulash, which are publicly available on GitHub. And these test a lot of the more esoteric integration that people might do, and intercompatibility builds. And then, of course, the OSU micro benchmarks, which are the best benchmarks. And proxy apps are run for performance regression testing. And then ideally, we would wait for all those tests to pass, and then we would just make the new MVAPICH available to users, depending on needs, et cetera.
Just a quick question. Can you describe more about the Goulash test suite? What does it do?
Okay, so Goulash does a bunch of, it attempts to build a bunch of very simple MPI related tests. So for example, GPU-aware MPI with OpenMP, and we want to do AMD and GPUs, and so it just sits there and tests all these wacky combinations that we've usually gotten tickets about in the past.
So is this a pure build test, or does it run some code as well?
Yes, it runs. Yeah, it builds and runs.
It builds and runs.
Yeah, and we have a couple of nowhere near as extensive as OSU benchmarks, but we have a couple of really quick and dirty, okay, run an all reduce and see if we get a reasonable latency, things of that nature.
So that's very interesting. So when you say reasonable latency, I remember that Adam used to have some scripts which would flag bad latency. So does this do that as well? For instance, for 2 nodes, 4 processes per node, do you have an expected all reduced latency, and does the test flag it if it fails that?
Yeah. Yeah, yeah.
Okay.
So we do things like that. Yeah.
Okay.
Yeah, and Adam's tools were
MVAPICH.
a little bit more extensive. That he would even have like find slow links and stuff, which is more fabric related. But we would see if there's like something really really wrong in the fabric configurations as well.
Okay.
And we can build and run those. Ideally, we would do it all, right? So we get performance regression testing and functionality regression testing. Yeah.
Okay, cool. Thanks. Please go ahead. Thanks.
So in order to do all of this, we're going to use Spack. Spack has been introduced here before. The GitHub is there in the QR code. You know, Spack allows for a very high degree of build precision with a relatively simple syntax that the end users can generally use reasonably without having to understand a lot of the inner workings and gory details of HPC. It's widely adopted. We have a lot of contributors worldwide. So, you know, upstreaming allows people to sort of, especially when you upstream package information, allows you to go ahead and let other users benefit from all of the things that you've bumped into building on a particular system. So that's one of the great things about Spack. And we've already done a lot of work with Cray, especially Cray compiler stack, to be able to make sure that we upstream that stuff too as we bring our new systems online. So even a month of development is very busy. And so just to do some updates on Spack that are a little bit relevant to what we're trying to do here. So we have compiler runtime dependencies that are properly modeled. You've probably seen the GCC runtime appear in your DAGs if you've been building with Spack. We have, I'm going to go through these quickly because we're going to get into more detail later. Improved find UI, conflict and prefer syntax for package preferences. Environments can include other concrete environments, which is big, and I'll go into a little bit later. And we have, you know, virtual environments for Python, that sort of thing. So the big news, and Samir had already pointed this out, and it's great. We've officially become a Linux Foundation project. So this has a lot of implications. You're no longer contributing to a Livermore project when you contribute to Spack. You're contributing to a neutral legal entity. There's no need to you know, this helps really jump a lot of legal hurdles that folks had contributing to Spack, especially people from outside the United States. So this has been a benefit, I think, and it's going to overall be a benefit to the project. We're going to see a lot more contributions. So underneath the Linux Foundation, you know, we've jumped in with a bunch of other projects with the High Performance Software Foundation, or HPSF. And so this was officially launched at ISC. And so this is a nice group of members. We have a lot of different industrial and academic and public members here, along with some integrators. So lots of energy behind it, and we have a lot of projects. And so coming soon, we have Charlie Cloud, but we have Spack, Cocos, WarpX, Aptainer, E4S, HPC Toolkit, Trillianos. Just to name a few, and we're gonna have I think a lot more. I think this is very likely to grow. It's kind of a win-win. I won't get into the gory details of how it operates, but you know, it does allow us to have these partnerships with Cloud Native Computing Foundation, Open Source Security Foundation. We can sponsor events. You know, it's a great way to introduce adoption contribution of HPC software. Okay, this didn't come out correct. Okay, good. So let's jump in. So this is getting into some of the more gory details of Spack. So Spack is you know, based on a concretizer. The concretizer takes your description of what you want to build, and it turns into what we call a concrete spec. So it comes from an abstract spec to a concrete spec, and in that process, it comes up with this is where it applies the precision of exactly how you're going to build. This is done in answer set programming, and it's kind of black magic in a sense that this, you know, kind of shouldn't be solvable, but it is. But these facts, which come from package PY and variant values, get processed through first order rules, and that can resolve nodes and metadata, and that can help build out a DAG, and then you can actually figure out how to Spack will figure out how to build. And so this is great because you get very precise builds, and you can get ideally reproducible builds. The problem that we've bumped into is that the sort of the nature of how Spack was designed from the very beginning was that it was designed to be really built from source. That was really kind of what was considered the ideal. And that was, you get to ensure ABI compatibility, but in a lot of cases, it's a little bit overboard. And here's an example. So you have GPTune, you have PyG event, you have PyNumPy. Spack will detect that there is a build dependency on PyCython. And so then what it's going to do is it's going to say, it's going to hold back this G event to a very old, not a very old version, but an older version that it could build because it's going to need to pin that dependency. And as we know, this doesn't really matter because the Python, ABI doesn't exist. It's Python, so it's an interpreted language. You don't actually need to make sure that you built the packages with the exact same Python. So what we've done is we allow for separate concretization of build dependencies. So this now frees up G-Event to be able to use its version of PyCython. PyNumPy can use its version of PyCython. Everybody's happy. That way, we can actually relax some of these constraints with these unification sets that we have. And so this is more Gore details about how this kind of works. So we allow the solvers to choose a duplicate node. Is how we did this in code. So now instead of having a single node, it actually has a selection of a list of nodes, and then it will make sure that the dependency still holds. In order to do this, of course, we had to change how the nodes were identified. We had to use both a name and a dep node ID. So that's kind of how that works. And so this is all moving towards being able to recycle binaries more effectively, right? Compilers can now model their own runtimes. So you can take libstandard C++ and Fortran runtime compatibility into account. Intel compilers now correctly depend on GCC runtime, so you can actually see this in the DAG, and the concretizer can reason about it, and that's a big benefit that will help make sure that we can reuse binaries as much as possible. Languages are almost virtuals. So in the example shown here, C++ or CXX, can be defined as a language. For those who aren't familiar with virtuals, so like MPI is a virtual, OpenMPI is, or MVAPICH, or these are all implementations of MPI. So we can now do the same thing with like CXX Fortran. So we're moving towards this so that you don't necessarily have to specify all of these at build time. And we'll get into this because what it allows us to do is, again, have different binaries and be able to model whether or not they are ABI compatible. libc is also a virtual now. It can be external or built by Spack. It's probably going to be external. Hopefully you're not building it with Spack. But this allows us to, again, get many more binary build cache hits because you're able to, again, the concretizer is able to reason about it, and we can say, okay, that's either important or let's just throw that away. It's not going to be necessarily relevant for ABI compatibility. Yeah, again, this is just showing building Emacs. Can now be built 100% from binary because we can now just say, okay, well, that libc is ABI compatible, so we don't need to worry. Okay, so this is a lot of the work that I've been heavily involved in, building and reusing packages in Spack. As I mentioned before, Spack errs towards building packages from source. And so, when we get into large packages, or even in the sense of what we're doing now at Livermore, which is building our entire development environment with Spack, it can take hours or days to do these builds. And not every package can even be built from source on every platform. For example, for Cray, MPI is always an external, so that you're not going to be building Cray MPICH from scratch using Spack. So users, can constrain Spack to use specific system packages for certain dependencies. This is used in your environment with the external syntax. So you go under packages, put external, and then you can say buildable is false. And so that's you constraining it. And so then the Spack concretizer will force it to build with a particular external. This will influence hashes. And then because this influences hashes, you are going to have mismatches in the hashes. And then, of course, Spack is the concretizer is going to see that the hashes have changed, and it will not allow you to reuse a binary that somebody else built with us, with any external, frankly, because it's going to influence. You're going to get different hashes. You're going to trigger a rebuild. So this is kind of the example of where we want to go. So on the left-hand side, we have in a build cache a binary package for HDF5 that's already been built, and on the right side, we have a binary package for MVAPICH that's already been built. And if you look very closely on the left side, you will see that that HDF5 uses the wrong MPI implementation. And the one on the right is the correct MPI implementation that we would like to use because we're at MUG. And so the idea is we want to get to the purple one, which is the spliced one. So we know in this particular case that, so this is left out of the picture, but we know that this MPICH and this MVAPICH are ABI compatible, let's say, because we know that MPICH and MVAPICH are generally ABI compatible between the correct versions. We know the zlib is ABI compatible, so we don't need to worry about that, right? The problem is that in the existing Spack implementation, the concretizer has no way of knowing this, and so it won't necessarily come to the conclusion that, hey, wait a second, I have binaries. Why am I rebuilding HDF5 from scratch? That's a huge build. I could just use these. I could just relink, basically. And so we developed splicing to allow Spack to do this. But critically, we maintain build provenance. So the spec.json metadata file, which hopefully you never have to look at, that Spack maintains in its store, is actually going to get updated, and it's going to have like this knowledge that this HDF5 was actually kind of a Franken HDF5, and so that way, if there's ever an issue down the road, we can unroll all the way back to the original packages and find out what happened and what went wrong. So that's the kind of code I worked on, mostly at the metadata level. The rewiring code for actually relinking is already heavily implemented in our relocation, for binary relocation in Spack, and it involves a lot of extremely gory stuff with like patch elf and going through and finding arbitrary strings in a binary and then replacing them. But that's already built, so we kind of leveraged it. So the issue is, how do you describe that those particular two MPI implementations are indeed ABI compatible? Well, you can express these constraints in the existing spec syntax. We are adding a new variant, or a new variant. We're going to be calling it can splice for now. Don't hold us to that. We might change the name once we actually go into production. But this will allow package maintainers to be able to declare when one configuration of a package can be spliced in for another one. And so it's going to be pretty powerful, and it's going to allow us to try to reuse a lot of builds. So we have some steps that we have to do to get splicing into Spack solver. There have to be rules added. We have to change the encoding of packages to allow for flexibility in splicing. We have to allow logic for the solver. We have to add a logic for the solver synthesizing splices into installed packages. And then we are going to do the rewiring. Again, the rewiring is pretty much done. It's just all of the work in the solver that we have to do to allow it to reason about relaxing the ABI constraints that Spack currently has. So, we would want to, again, be able to rebuild packages using a local MVAPICH. And I'm giving the example here of like GDR. So like, suppose you want to be GPU aware. We want to be able to do that. And we want to be able to do it in place without doing huge rebuilds. This is implemented in testing versions of Spack. The thing that comes up, of course, and we're being very sensitive to, is that Spack concretization is already not exactly the fastest thing in the world. And so we want to make sure this feature doesn't create a slower concretizer for everyone, whether or not they use the feature. But our initial testing here is with all of the Radius or open source projects at Livermore, and we see that there isn't any particular effect. The bar in orange is with the new feature added. It's not necessarily any faster or slower, I think, than the existing develop branch. So far it looks good, but we're going to continue to watch this to try to make sure that we don't slow down the concretizer. So that's kind of future roadmap. Getting back to, if you are actually going to go ahead and try to build an environment for users with entirely with Spack, there are advanced features that I want to call out that have actually been in Spack for a while, but a lot of folks don't necessarily use them, like matrix, so that you can do combinatorial builds, and you can describe these in your environment files, and view projections allow you to create a simpler, familiar user environment. So when people have, if someone really wants to hard code a path to a particular dependency, and they don't necessarily want to use Spack, because that's kind of the issue for us, right? We want to be able to create, at Livermore, we want to have an environment where if you're a user of our clusters and you're a huge Spack fanatic, great. If you don't necessarily want to use Spack, you can still do things, with LMOD and any kind of way you want. And so view projections allow you to do that. But for those people, those users you have who are Spack fans, included environments really boost the reusability. One of the things we're playing with now is this new feature allows you to include a concrete environment in another environment. So if you think about that, you could take your development environment that you've carefully built and curated and made sure that is highly optimal for your system, and you can hand that to users and say, here, include this environment, and then once it's all built and installed, and obviously once installed, it's been concretized. And then your users can take that and they can include it in their environment by simply including this absolute path. And then they can take that environment and then they can build on top of it. And so Spack, the concretizer, will automatically reason about this. One of the things that we bumped into pretty early on was that we need to try to parallelize the building as much as possible. And so and this is the work that Nick Sly has been working on heavily at Livermore, is we want to use containerized builds with Spack. And Nick has done a pretty good job of finding a lot of interesting ways of doing this. Just to throw out an example, I just checked here. We have 36 ROCm versions available on our LCAP clusters, because we've been pushing back and forth. Every time we get a version that fixes a bug, and we find another bug, and we get another version. We determined that this isn't really going to be, especially once we've tried to do GPU aware builds, we're not going to be able to do this in one giant monolithic build right on the metal. So that's kind of the reason for using containerized builds. The GitLab ci.yaml is on the bottom left here. It has a combinatorial parallel pipeline that is parameterized, and it creates both a parameterized Spack.yaml environment file and a parameterized Docker file. And so then we create many, many of these, right? So there's tons of Docker files and there's tons of environment files that get built. And then what that allows us to do is we can then send that to GitLab, and we can do parallel pipelines. So for example, when building MVAPICH, as we have here on the left side, we have a GitLab CI.yaml, and then that generates a bunch of these builds on the right side, half of which, the ones that are cray, are not working. And that's because I think the system was down that particular day when this was kicked off. But what's cool about this is it allows us to build and test not only different MPIs at the same time, but we can also build MPIs while the compilers are still testing. So the compiler's done building, and then there's another stage where they're going to be testing, but we can go ahead and we can just start building the MPIs on top of those compilers right away. Ditto for the MPIs, and you have MPI dependents. They can also start building while MPI is finishing its testing. So the idea is that, you might think, well, that's great. You're using containers, you're getting these binaries. Who cares? What isn't the container going to throw the binaries away, or are these binaries going to be trapped in these containers forever? No, because what we're going to be doing is, or what we do is the container is generated and it launches with given parameters. It mounts a binary cache that's already on the system, or in some place on like Lustre, and then the binary is built with Spack, and then the resulting binary is copied back out to that binary cache, and again, it's just relocated back to that binary cache using Spack, Spack's built-in functionality. It's been there for a while, and then future containers can then continue this process and get the binaries. And so we think that this has a lot of benefits. We're going to have precise, reproducible builds, ease of automation, verbose logging of dependencies, compiler flags, et cetera. And for cybersecurity concerns, build precision allows for us to create software bills of materials, also known as SBOMs, and see exactly what's running on our clusters without having to just hope that that RPM was built correctly. And that's all I have. Let me know if you have any questions. Thanks.
Thanks, Nathan. Great talk. And the things you're working on are my number like 1, 2, and 3 complaints with how Spack works, because we try and fit everything onto a node local image in 100 gigabytes, and it builds so many near copies that it's great. But could you go back to your HDF5 example slide real quick? Yeah, so in this case, you're resplicing and making essentially your new HDF5 star. Is the old one still visible? Because undoubtedly there'll be some application that breaks after you do this resplice, right?
Yes.
So even though 99% of stuff will work with the new version, there'll be one user somewhere who's, yeah. So they both exist at that point?
Yes, they will both exist. You will still have all the old ones available, and then because we maintain the build provenance, we'll be able to, you could roll back, et cetera. So yes, so that the idea is to have this just keep getting, you'll just keep getting a bigger and bigger install.
Yeah, but I don't have to rebuild all those things in that chain, which is probably a lot bigger than the graph you show every time we do a new version, right? So, and that's awesome.
Yep,
so
that's the idea.
And just one other quick one. How close are you to the vision that you laid out in the first slide for these fully automated MVAPICH upgrades?
We're actually pretty close because as I showed on that other slide, the builds are kicking off. We've run into some issues trying to get this working with Cray, but we've made some progress.
Yeah, I'm not surprised.
And so, this is, I think, pretty close, and I think it's going to be. Well, I don't want to give exact time estimates, but we have a lot of things already working, so we haven't hit any big showstoppers since we've run in this. But it also is, it's very important now, is one of the things we've realized, to make sure that for package maintainers that the package PY files are like for sure good to go, especially that we would be able to describe older builds with new package PY files as Spack continues to move. So like we've hit that as an issue and make sure we don't break things. But aside from some of these operational issues, I think we're pretty close. Yeah.
If you ever feel ridiculously ambitious, most of the time when we're pushing out an MVAPICH update, we're probably pushing new network firmware, to the InfiniBand card or something at the same time, or some other sets of patches. So if you wanted to manage firmware along with the software to get all the way to the end, that would be cool.
Yeah.
But also really hard.
Yep, for sure.
So let's thank the speaker again, please.